Welcome to this IMS conference session today. It will be on overview and best practices of tuning IMS data entry databases, so that's FastPath databases. Now, just to tell you that this session will be recorded and playback will be available at the end of the conference. There are slides. So there's no video, it's all slides, and those should be available to download as well. In terms of, there's a raffle that we've got. You can do a link to the raffle on the website for the conference, and it's a version Just Giving page. And to enter the raffle, you give a donation to, and those will go to Guide Dogs for the Blind and National Lifeboat. In terms of questions, questions format for today is, can we have them post them online in the chat? You can post them to all or to me personally. And what Aditya and Anshul will answer these at the end of the session, and then we can open up verbally for questions at the end as well. In terms of feedback, then please, there's a QR code in front of you just on the screen here, bottom left. So if you go on that link there, you'll find feedback link, and you can do that feedback after the session, and that feedback will be welcome. Alternatively, if you go onto the agenda website, then it's available. If you click on the avocado green color session, which is for overview and best practice, if you click on the title, then you'll get the link to the feedback link as well. So I'd like to just introduce the speakers for you today. So first off will be Anshul Agrawal, and he's from BMC, and he's a senior product developer and has been developing on mainframe for 11 years, and is currently working on BMC Army FastPath utilities. And then Aditya Srivastava is BMC, and he's got 13 years experience with mainframe, and he is a specialist product developer, and again is currently working on the BMC Army FastPath utilities. So without further ado, I'll hand you over to our speakers. And I think Anshul is going first. Thank you.
Okay, good morning, good evening, and good afternoon, one and all. Welcome to our session. So myself, Anshul Agrawal, and today I have with me Aditya Srivastav, who is my colleague, and we are from BMC Software R&D Group from the FastPath team. So today we are going to talk about overview on the best practices of tuning IMS data entry databases, which is FastPath databases. Okay, so we are going to talk about the overview of DDB analysis and the tuning. So it will basically consist of these 4 parts. We are going to cover the understanding of different parts of DDB area. So it is of paramount importance that we understand how these different parts are configured, because that plays a critical role as far as the performance of your database is concerned. Then obviously we are going to discuss about the tuning factors, what are the typical performance characteristics, and what are the criteria which should trigger you to tune your database, because maybe over a period of time, after a lot of data being inserted, your data may not be tuned enough to perform well. So in that case, what could be the criteria to trigger those tuning activities? So as far as IMS is concerned, one thing we must know is, it is using something called Media Manager, which is specialized IO channel programs, and that is specially designed to perform very fast and do IO very, very quickly. So that's a proprietary IBM software, which is a Media Manager, which is what IMS use to do all the IOs and to do all the DL1 calls. You know, so as a user, it is our responsibility, as a DB, it is our responsibility to make sure that from time to time we review our data, we review our databases, we review our areas and see if there is any opportunity to tune those databases to gain the actual advantage of using fastpath database, which is supposed to run very fast. Okay. So as I mentioned, the very important thing is to understand the different parts of DDB area. So there are primarily four different parts in the DDB area. One is the root addressable area, then there is a dependent overflow area, then there is an independent overflow area, and then there is a sequential dependent part. So DDB area is nothing but one single VSAM ESTS, and on top of that ESTS, there is a structure which got laid out which IMS is calling DEDB. So that structure is basically consisting of these primary four parts, that is root addressable area. So whatever your root segment will be, it will be used by the randomizer and it will be directed to particular RAA. And then if RAA does not have enough free space, it will have a dedicated space which is called DOVF, which is connected within a particular unit of work. So if your root segment cannot be resided there, it will go to the overflow part. And if there is not enough space in the overflow part, there is a common storage pool. There is a common storage, you can say, which is IOVF. And when certain CIs from IOVF are allocated to particular UOW, then it will be allocated to that particular UOW for entire lifetime until you do a reorg. And probably by that time, those CI might become free and it could be reused further by some other UOWs. And then one of the very unique feature of DDBs is step. Uh, this concept is not present in any other database, full function database in IMS. This is a very specific fast path concept where you can do very fast insert and scan all your data to a sequential file and feed it to downstream processing for further processing. So it's more like a journal processing where you don't want to insert a lot of data, and you should have the ability to access that data very fast. Since they are directly linked to the root segment, it is very accessing those step segments is going to be very fast. Okay, as I mentioned, this RIR part is the basic unit of overflow, and this is the basic unit of your free space reorganization. So when you look at the VSAM ESDS, all those RRA and DOVF part is called one unit of work, which is basically the unit of work for any vendor utilities when it processes certain data. Then this UOW is further divided into base section, which consists of RRA part, and then there is a overflow part, which are basically the CIs which are dedicatedly allocated to certain UOW. Okay. So all these CIs in RRA and DOVF, they are continuously allocated in the storage. But talking about the IOVF, they are not continuously allocated. They are further down the area, and it is kind of a common pool, and the CIs from this common pool gets allocated to certain UOW on a need basis. And once it is allocated, it will remain allocated there. We are going to look into this diagrammatically, so it will make more sense. So in the coming slides, we are going to talk about that. And then I mentioned about the S step. So whatever the size of your data set on the DAS-T, that will define what will be the size of your S-step portion will be. Even if your database does not have any S-step segments in your DBD, it is still possible that the rest of your area is formatted as the S-step portion depending upon the size of the area. So how all these 4 or 5 different sections get configured in the area basically determines or governs what would be the how well your database is going to perform in terms of physical IO. So it is of paramount importance also from the generic perspective and also from the performance perspective to understand all these different sections and understand how they are used by IMS in a DDB area. So I have taken a very simple sample of a area dataset layout. So this is how it looks like. It is a single VSAM ESDS. So if you go by this definition, it has a size which is the CI size, which we have taken as 4K. Then there is a UOW parameter, and then there is a root parameter. So if you look at this, it is a collection of CIs. And the first CI is the VSAM over at CI. Second CI is the DMAC. So DMAC is basically a kind of control block which contains the information about the entire area and the different boundaries. So if you look at these boundaries, or kind of, these are different RBAs, which defines from, okay, from this RBA to this RBA, this is the particular area. So if you look at DMAC HRF, it is basically the starting portion of your RIA. Then if you look at the DMAC FOVF, it is the starting portion of your IOVF section. So these are different pointers which are stored in DMAC, which signifies, okay, from this particular physical RBA, this section is going to start. So if you look at that, if you look at the root parameter, which is 14,4, which basically signifies that out of these 14, 4 will be your overflow UOWs, which will be part of your IOVF, and 10 will be your base UOWs. And within the base UOW, you will have a UOW parameter which will define how many CIs will be there in RAA section and how many CIs will be there in the DOVF section. So if you look at the UOW parameter, which is 9,3, it basically signifies that within a single UOW, you will have a 6 RRA CIs and 3 DOVF CIs. So talking about uh, choosing the right size of the CI, right UOW parameter, and right root parameter is of paramount importance as when you talk about the performance of your area is concerned. So let's say the different CI size which is allowed is obviously 512 bytes, 1K, 2K, 4K, and then in multiple of 4K up to 28K. So choosing the optimal CI size is of paramount importance when performance, as far as performance is concerned, because if you choose a very large CI size, then there is a possibility that when you use the some vendor tools like online reorg, they always work on a UOW basis. So if you have a very large UOW size, in that case your reorg utility might be holding that UOW, and it might cause contention to some other transaction which might try to access the same UOW. At the same time, you do not want your UOWs to be very small, or CI size to be very small. In that case also, when these utilities will work, it won't do much work switching from one UOW to another UOW. Also, one more important thing to consider when you choose your CI size is the average record length. Because if the average record length is more than the size of CI, there is a possibility that segment will not get stored in CI, and you will simply run out of the space even when there are a lot of space in the area. Then coming to the root parameter, again, it is very important that you choose a very right set of root parameters, because that basically signifies how many IOVF CIs will be there in your area. And that is the only portion, including step, which can be expanded online, which can be extended online. So if you choose such a root parameter that won't give you a room to extend your IOVF or step section, then you may run into some kind of trouble. So again, when you design your areas, you need to have the knowledge of your data, and on the basis of your data, you need to choose the size of your CI, UOW parameter, and of course the root parameter. Then there is one thing you might notice in the end is reorg UOW. So that is something which is there just for the compatibility purpose. In very old ages, when this was introduced, it was used by the IBM reorg utility, but later on they have gone away with this. So it is right there just for the compatibility purpose, which is just a waste of space. And of course, in the end, you have your step CIs, which basically depends on the size of area. Even if your DBD does not have any step segment, you will still have the step section, although that step section will not have any step active step segments. Okay, so we were talking about these CIs, these different sections, and in these different sections, it will have these many CIs. So what exactly is there in these CIs or block? We use this term block or CI uh, alternatively. So what exactly this contains? This basically consists of these five things. It will have a header, it will have a footer, or we call it trailer. It will have a segment, it will have a free space element, then it will have a scrap. So as far as segment is concerned, it will have a segment code byte, which is a 1 byte code, which will signifies the number of segment, the different segment types your database, your DBD might have, or your database in question might have. So it could be from 01 to 7F, which is obviously 127 in decimal. But if you use the S step, you could only have up to 126, because if you have the step segment type defined in your database. Then the other part in the segment would be your segment prefix, and of course the actual segment data. Then the very other thing is free space element, which is something which is used by the IMS space search algorithm. Whenever it has to insert some data or segment, it will go to the free space element, and that free space element will have a pointer to the next free space element, and then it will also will have a size which should always be 4 bytes or more, because whatever we have which is less than 4 bytes, we call it scrap. And then whatever the space is there in the free space element, it is always cleared to 0. And and within the free space element, if your space is less than 4 bytes, which is 3, 2, or 1, we call it scrap, and they are basically initialized with these values, either f1 or 7.1 if it is 1 byte scrap. If it is 2 byte scrap, it will either be f2 or 7.2. If it is a 3 byte scrap, it will either be f3 or 7.3. So if your database has segment type 7 or less, it will be initialized with 7.1, 7.2, and 7.3. But if your database has segment types more than 7, then it will be initialized with f1, f2, and f3, and so on. Talking about the block header, these are very important flags or fields which are there in the block header. And as a fastpath DBA, or as a fastpath person, you should be having a knowledge of this. Although maybe from the application perspective, we don't care, but still having the knowledge of what different flags, at least what important different flags or fields is there in the block header is pretty important. So the first 2 bytes is basically the offset to the first free space element. So within the block, whatever the offset, whatever the free space element is there, what the offset to that first free space element will be there in that block. Then there will be 1 byte of block type. So it could either be any kind of block. So we have talked about the wrap block, which is RRA block. Then it could be a DOVF block, it could be a space map block, it could be IOVF block, or it could be a step block. Then there is a 1 byte flag. Again, for DOVF block, there is a bit setting called look here flag, which is again used by the space search algorithm. So whenever IMS has to store some data in the DOVF, it will go to the first DOVF and look at the look here flag there. And then there is something called uh, whether the block has cousin or not. So in the block trailer, there is something called cousin, which is your RBA sequence number. So whenever your CI gets updated, this cousin gets incremented. So whether this particular block in question has that sequence number or not, this flag basically signifies that presence. Then there are either 4 byte fields or 8 byte fields in the end. For step, it will be an 8 byte field which contains the IMS subsystem ID. But for the other blocks, it is a 4 byte field. So for wrap block, it will be root anchor point. For DOVA block, it will be overflow chain pointer. For space map, it will be chain anchor. And then for IOVF, it will be UOW ownership. So as far as IOVF is concerned, as I mentioned before, IOVF is kind of a common storage, and the CIs from that storage gets allocated to UOW. So once it is allocated to certain UOW, it will be owned by that UOW, and that is what is meant by that UOW ownership. Coming to block trailer, it is these common 4 fields, and The first 2 bytes is a update sequence number, which is again optional, and depending upon that flag, that will signifies whether this block has a cousin or not. Then obviously the 4 byte RBA, and then two more fields, which is the RDF and the CIDF, record descriptor field and control interval descriptor field, which is 3 and 4 bytes respectively. These are not something which is primarily used by IMS. This is more of a VSAM generic concept. Talking about the free space element chain, so you can view this as a single block or a single CI, and the first thing is the block header, and the last thing is the block trailer, and in between you can see different free space elements. So if you look at the block header, it has an offset to the first free space element, which is FSC-1. Then it has a type to signifies what kind of block it is, whether it is RA block, DOVF block, IOVF block, or an S-step block. Then it has different flags and descriptor word, which we talked about. So that first free space element points to the that block points to the first free space element. That first free space element points to the second free space element. That second free space element point to the third free space element, and so on and so forth. They do not need to be continuous. They could be randomly present in the entire area. And within this free space element, if it is less than 3 bytes, less than 4 bytes, then we call it a scrap. And then you have the block trailer, which is the RBA, RDF, and then the CIDF. Talking about the dependent overflow block, so as I mentioned, within a single UOW, you will have the RRA block and the DOVF block, which is in the continuous storage within a single UOW. And the data which gets stored in that UOW is dedicatedly allocated to that particular UOW only. So whatever the DOVF blocks you have, they are dedicatedly allocated to that particular UOW. And for the next UOW, there will be dedicated DOVF blocks, and for the next UOW, there will be dedicated DOVF blocks, which is different from the IOVF, which is kind of a common storage which gets allocated to UOW on a need basis. So in DOVF, there is an important flag which is called look here flag. So that will be present only in your first DOVF block, because that is something which is used by the space search algorithm. Whenever it wants to insert some data, it will go to the first DOVF block and look at the look here flag to determine whether it has free space or not, so that a segment can be accommodated. And then there are two more important, it is only one pointer. So initially when your database is empty, this there is an pointer or an RBA in each DOVF blocks that points to the next DOVF block. But once the segment gets started getting stored in the DOVF block, that DOVF block may point to the IOVF block if there is not sufficient space in the DOVF to store any further segments. So over a period of time, your DOVF overflow block may gets full by storing some segments. And if you have a very long twin chain, the DOVF, it may cause performance penalty in terms of IO. So IMS provides a very unique concept, which is again unique to DDBs, that is called subset pointers. So subset pointers can be used to divide the very long twin chains into multiple portion, and there could be up to 7 different subset pointers on the same chain. And your application program can use those subset pointers to access the portion of change, and by that way, it can reduce the IO. Okay, talking about the IOVF block, uh, they are basically immediately following your DOVF blocks. So as I mentioned, these are not the dedicated storage. It's a common pool which gets allocated to certain UOW on a need basis. And as soon as the need is done, when you do a reorg, these blocks might get freed up. So we call one UOW, which is a collection of 120 IOVA blocks, and within those 120 IOVA blocks, your first block will always be a space map block, which basically signifies or determine, okay, in which different blocks within this UOW the free space is available. Two important flag to remember in this is block available and block allocated. So if the block is allocated is set, it means that it is allocated to certain UW. If block allocated is not set, it means that it is not allocated to any UW, and it is free to be allocated to any new UW to be processed. Okay, before moving on, One thing that I think Adit is going to talk about in the next part of the presentation is that there should not be a lot of segment which should go to IOVF. So it is of paramount importance that you choose the size of your IOVF to be sufficient in case you need to extend. But ideally, your segment should not go to IOVF. The less it will go, the more better your database is going to perform in terms of performance in IO. Okay, let's talk about the locate free space algorithm that IMS use. So let's consider there is a root segment and IMS invokes a randomizer to call randomizer, and your randomizer will say, okay, this root segment should go to area number 10, UOW number 17, and RRA number 3. So it will go to the RIA number 3. It will not, if it finds enough space, it will be stored there. But if it does not find enough space, it will go to the first DOVF block directly, and it will look at the look here flag. And if there is enough space, it will get stored in that DOVF block. But if there is not enough space, it will go to the next DOVF block and see if there is enough space. If it is not there, it will go to the next DOVF block, and so on and so forth. Let's say it reaches the last DOVF block. In that case, it has to look to go into the IOVF block. So by that time, it will go to the space map and see whether this IOVF CI is allocated to certain UW or not. If it is not allocated, it will allocate that IOVF CI to that UW, and a segment will eventually get stored in that IOVF CI. Let's consider in the worst case, even in the IOVF CI, there is not enough free space. So eventually you are going to get FS status code. So imagine the role what randomizer has to play here. If your randomizer is badly designed, it might always direct these segments to go to certain UOW, certain area, certain UOW, certain RIA, and you may run into occupying all the DOVA blocks, IOVA blocks, and you may run into FS status code. Although it is a possibility that you might have 80 to 90% free space still available in your area, and you will still get the FS status code. So your the design of your randomizer is of paramount importance in this situation. Okay, let's talk about the S-step portion. As I mentioned, this is the unique feature of DDBs, and it is not available in other different IMS databases like full function database. Especially in a data sharing environment, S-steps are not difficult, not easy to understand, but the way it works is very seamless. So this is the portion of the area which is towards the end after the reorg UOW. So again, as you can see that there are some pointers in the DMAC, which is DMAC FSCQ, which is signifying the start of your S-step portion. Then you have the DMAC FPAD, which is the end of your S-step portion. Then you have logical begin and logical end, where actually your S-step segments are residing. So as and when your S-step segments gets inserted, your logical end will move further. And after reaching to the end of area, it will start wrapping it around, and your S-step segment will start getting inserted from the DMAC FSEQ, and it will start wrapping around one after the other. So this is the condition of the wrap. In that case, your logical begin RBA would be greater than the logical end RBA, and you will have a different cycle count. So it's pretty simple to identify whether your S-step portion is wrapped or not. Simply look at the logical begin RBA. It will be greater, and your cycle count would be different, because generally the S-step pointers are the RBA plus the cycle count, which is the 8-byte pointers. As far as the S-step processing is concerned, these are the different DL1 calls which are allowed. You can only do the get next call, or you can only do the mass insert call. You cannot do a replace or delete call. And when you do insert call, it logically advances your S-step logical end further, and they are stored in the chronological sequence. It does not depend under which route your S-step is stored. It will always be stored in a chronological sequence. And whenever you delete a root segment, it will cause your S-step segment to become an orphan S-step segment. And even if you defined it as a delete cascade, it is not going to delete your S-step segments. So IBM provide these two utilities, which is step scan utility and step delete utility. So whenever you do the mass insert, and after doing the insert, you need to use the scan utility to scan off all the data from the step section to the sequential file. And then you will use that sequential file further in your downstream processing to process further. And then you will use the delete utility that will simply reset your pointer, the logical begin pointer to the logical end, and you will have all the space in the step to be used further. So this is how your area or the step portion looks like before the scan and delete. You have the logical begin and logical end in an unwrapped situation. And when you run the scan, it will scan all the data from the logical begin to logical end and store it into the sequential file. And when you run the delete, it will simply reset your logical begin to logical end. And now you have the entire space to be used again in the step section. Okay, talking about the performance characteristics of step. One thing to remember here is in IMS uses something called step buffers to store all the step segment initially. And whenever the step segments are committed, they are not returned to DASD. They are kept in the step buffer. Okay, so let's say there are multiple transactions which are doing which are writing step segments, and they are committing step segments, but they are not returned to DASD. They are kept in a buffer, and whenever your buffer is full, at that time only IMS is going to write those step buffer onto DASD. So that way, what IMS is doing is it is accumulating all the segments in a single buffer and doing IO only once. And by doing that, it is saving a lot in terms of IO. And that's why step insertion is fast. Apart from having the fact that it is directly linked to the root segment, uh, IMS uses these tricks to make step work very fast. Other important thing to remember is, especially in a data sharing environment, if you are using step, IMS uses a concept of something called pre-allocated step CIs we call packies. So whenever those things are used, it is possible that in a data sharing environment, some of your IMS might be inserting at very fast rate, but some of the IMS might not be inserting at that fast rate. So in that case, that particular IMS which is not inserting at the fast rate, it might hold up your step portion. So in that situation, IMS provides one feature called automatic step buffer management, where you can set certain frequency and date. By that time, IMS will flush those things out, and you will not face any kind of contention. Then again, to handle this situation, there is something called quit CI processing, which is available with the scan and delete. So whenever you run scan and delete, you can use the quit CI processing, and it will give up on those packies and harden that to DASD. One more thing, if your area is using multiple volumes and it spans across multiple volume, try to make sure that your step is using a single volume. So whenever the media manager or the IO channel programs, it has to deal with only one volume, it can save on the seek time. So that will help you gain some performance in terms of IO. One more thing to notice, or to make a note of as far as steps are concerned, uh, try to dedicate a root segment to some terminal or to some transaction and insert a step under that root. That way you can avoid some contention, because there is a possibility that multiple transaction might be inserting in the same root and they might be locked. So in that case, you may face contention. So it is recommended that you dedicate your root segment to certain transactions or terminals. And of course, once you do all the insertion, you will use the scan utility that will scan off all your data to sequential file. But once you scan it to sequential file, you should have some mechanism to match your step segment to root segment. Because in your sequential file, you will not be having any clue. Okay, this particular step segment belongs to which particular root. So in that case, you should have some data in your step segment which can help you to match the root segment once you scan it off. Again, that's something which is the application specific thing. But again, I think most of the shops which uses the step, they have this concept. Couple of other things that I want to mention as far as performance is concerned. If your DASTs are over allocated, if your area is over allocated, when these sections are unused but they are over allocated, it also causes problem to IO channel programs, and your IO could be impacted in that case. And one more point is about using multiple area data sets. So when they were introduced at that time, DSTs were not so reliable. So people used to have up to 7 copies of areas, but that will be a lot of overhead on IMS because it has to keep all the 7 copies in sync. So it is of course a lot of IO. But obviously in the recent times, the STs are more reliable, and customers or most of the folks they are going away with using mats or maybe having only 1 copy to basically overcome the overhead of maintaining multiple copies, because obviously IMS has to keep all of that in sync. So basically all these points like different sections, step, uh, how you configure them, you should have the knowledge of your data. And it is also possible that when you design this stuff, your data is something else, but later on, after few years, the characteristic of your data is changed. But we as a DBA or as a fast path person, we tend to ignore that fact, and we do not pay a close attention. So there should be some mechanism inbuilt which can help us, or at least remind us that over a period of time we should look at these factors. And by doing some tuning or changes, we can definitely gain some performance as far as IO is concerned, because fastpath is all about performance. Okay, I think that's it from my side. I will hand it over to Aditya to take us further to this presentation, and do a little bit deep diving onto the performance aspect of it. So Aditya, I can do a transition of slides for you, but you can do the commentary from here.
I'd just like to say thanks, Anshul, for that.
Okay, yeah. Thanks, Anshul. And good morning and good afternoon to everyone. Anshul, can you please put on the next slide? Okay. So far we have seen Anshul talking about different sections in our DEDB database, and he has also touched upon few of the best practices that should be followed in order to keep your database healthy. I'll be talking about more about the tuning factors, and also we'll see some snapshots of reports, and then what are the different threshold values. So tuning, when we talk about tuning, DEDB tuning is more of a subjective process. The tuning decisions that you that we have to make, it depends upon how the application activities are being performed on the DEDB, and also on in future, what do we expect the activities to be. So in general, there are 3 key factors which contribute towards a tuned database. The first from that is utilization of the free space in that area, in the DEDB. The amount of free space within each area of a database and the distribution of that free space has to be monitored on a regular basis, and that is needed so as in future we can avoid any out of space situations. That also helps to determine what is the right time for you to tune your DEDB. So in order to get the maximum utilization of free space after a reorganization, it is very important to understand through the various reports how do you need the free space, and then use a proper tool to gain those. The second point in that is, how do we define the CI, the CI size, the unit of work, and the root parameter? And these has to be defined in such a way that the movement of records into the overflow can be reduced. We don't want a lot of our database record to be in the overflow section that increases the IO. Talking about the CI, I mean, in general, if we have the average database record length, and if you multiply it by the number of root segments on a wrap, and if that value is less than the current value of CI, then that is fine. But if that value exceeds the CI size, then probably it is a good time to have a look at different reports and revisit your CI size, your UW and root parameter, and also maybe the how the randomizer is performing basically. So we have option to choose a CI size starting from 512 bytes to 28K bytes. But a very small CI size that will cause an increase in the IO, thereby decreasing the performance of the DEDB. And if we select a very large CI size, then there is a chance that we might get larger synonym chains, and again that is also not good for the health of a DEDB. The third part the third of the factor is basically how efficient is your randomizer. So randomizer efficiency is also important. Tuning the randomizer to optimize the utilization of RepCI, and also minimizing the overflow of database records. So the selection of randomizer that best matches the key values of your database record, that is of paramount importance from the aspect of database design, DEDB design. If we use a randomizer that does not matches the key value, that can significantly cause degradation of the performance of a DEDB. It can also add up a lot of synonym chains, which takes a lot of IO. So when we talk about randomizer, there is an example which we take kind of an analogy. We consider a very big building which has several rooms in it, and then there is a gate. There is a person who will receive the guests and allocate a room to those. Let's say guest 1 comes, he goes into room number 4, or guest 2 comes, goes into room number 4, guest 3 comes, who goes into room number 4. So basically the person is allocating all the guests to a single room, and after a while that particular room will get full. Okay. So talking about this analogy, we can consider that person to be a randomizer of your DEDB, and that particular building to be an area, and that room to be a RepCI. Now we don't want that a randomizer should continuously put all the record into a same a RepCI and causing long chains. So where you do have free space in this particular case in your area, but again, since your randomizer is constantly putting all the records together, at some point of time you might need to add more IOVF to your DEDB. So this is not a desirable result. Anshul, next slide, please. Okay, so talking about a typical performance characteristic, a tuned DB, if we have a tuned DEDB, it will not use the IOVF. I would say it should not, or it should, at a minimum, it should use the IOVF. So no or modest use of IOVF section. The percentage of unit of work that uses IOVF should be very low, or if possible 0, but that is not practically possible. The average and maximum number of IOVF CIs that are used by the UW should be low. And of course, the percent of database record which are being used by the IOVF should be low. So IOVF should not be used if you have sufficient free space in your DOVF section of most UW, because once you have your IOVF filling, that amount of the number of IOs it takes to retrieve that particular database record, it increases. Next slide, please. Okay, now this is sufficient free space in RA for each unit of work. So basically the percentage of free space in each section of the area, that is a RA base, the DOVF and the IOVF section, that should be sufficient after you do a reorganization. We need to have sufficient amount of free space, especially in the IOVF section, which we want that maximum free space should be there. It should not be the case that there is a chance of utilizing entire of space, available space in future. And the second point is that if there is sufficient space in your DOVF, we have to keep sufficient space in our DOVF so that the utilization of IOVF can be minimized, because we don't want IOVF to be used. Next slide, please. Okay, so Now, another aspect is that we need to minimize the IO. So the average and the maximum physical IO which it takes to retrieve a root segment, that should be minimized as less as possible. And the average and the maximum physical IO that is required to retrieve a database record should also be few. If we can reduce the number of IOs, then the performance can be increased. So when we talk about tuning a DEDB, the important aspect is that all these criteria should be satisfied as much as possible to get the best performance out of your DEDB. Next slide, please. Okay, so these three factors of a tuned, I would say, a characteristic of a tuned DEDB. I mean, based upon those, there are certain indicators, there are certain criteria which we'll see in further slides as well. And out of these are the 6 criteria which should be monitored regularly in your DEDB to get the best performance out of it. First of them is the overflow usage, how the overflow is being used, especially the IOVF portion. Then come the free space availability. Is your area has free space, and then come the free space relationship. So at times you have free space available, like in the example we have seen about that particular room, you have a lot of free space available, but at some point of time you will need to add some more because the free space is not utilized properly. So the free space relationship is also important. You need to have proper free space in your RA and IOVF and IOVF. Then how the root IO happens, the record IO happens. We need to reduce the root and the record IO of our DEDB. And then the last one is the synonym chain. I mean, if there are long synonym chain in your DEDB database, then that will cause performance issues. That will cause more IOs and thereby reducing the performance of your DEDB. Next slide, please. Okay, so in the slides to come, we'll see how certain reports will indicate that your DEDB might be in an untuned status. So we'll see some of the snapshots of analyzer report and try to see what factor is there which might be indicating that our DEDB might not be in a healthy state and there might be a need to tune that particular DEDB. So we'll see the sample of report. Next slide, please. Okay, so this is a snapshot from the overflow free space element analysis report, and it has a lot of details in it, but we'll just focus on the lower half of this report. If we see this report, there is a UOW percentage section, and if we come at the bottom, I think last 7th or 8th line from the last, it says that around 97% of the unit of work is having less than 20% of free space, and so it means only 3% of the unit of work has more than 20% of free space. That is very less. Another thing is that it says that most of the unit of work which are using DOVF that are also using IOVF, and we need to reduce the usage of IOVF as much as possible. At the end, it says that almost 99% of CI which are being used are using UOW, which are being used are using DOVF, and out of that 97% are going into the IOVF section. So these numbers, these percentages are very high. It does indicate that the usage of overflow is too much and there is a scope for it, reducing that usage. Next slide, please. Okay, this is an IOVF space analysis report. It just gives us a snapshot of how the IOVFs are being used, and we can see that almost all the IOVFs which is present on this report, on this snapshot, they are almost full, and the remaining one are almost at the edge of getting full. So that means we are about to utilize the entire IOVF, and there is a chance that we might get a free, FS status code if we don't free up some space in IOVF. And so next slide, please. Okay, yeah. So this is a wrap versus overflow analysis report. It just indicates that almost, if you see this report, the CI usage summary report for wrap, it says that the 99% CI which are being used, that is currently using overflow, and one of the aspect of tuning was that we need to reduce the overflow usage. Okay, so it says that 99% of the CI is using overflow. We need to reduce it. We need to shrink the records as much as possible to be in the base. If you see the overflow CI usage summary report, again, the numbers are pretty high. It says that out of all the CIs, 100% UNWs are being using DOVF section of your area, and then the IOVF utilization is also 69%. So these numbers, I mean, these indicate that a higher utilization of IOVF section of the area, and we want to reduce that as much as possible. Next slide, please. Okay. So this is a free space and synonym chain analysis report. A free space analysis report, it gives you an idea of the amount of usable free space which is available in your different sections of your DEDB area. As highlighted in yellow in the free space analysis report, we can see that only 10% of DOVF section is having only 10% free spaces available in the DOVF section. And we can see that in the IOVF section, it is 25%. We, as much as possible, we want more free space in the IOVF and the DOVF section. Probably in such case, other report has to be looked on. More space need to, DOVF, more free space need to be added in the DOVF part, and IOVF record need to be moved into the DOVF part. We need to reduce IOVF usage. The second report, it just says that the synonym chain length, I mean, the average length of synonym chain is almost 3, and the maximum is 19, which is pretty high number. And if you also see that the IO, which is needed to read that synonym chain, that grows up when the synonym chain increases. So another aspect is that we need to reduce the synonym chain, and the randomizer plays a role in that. Next slide, please. This is a record placement report. It just indicated what percentage of what percentage of records are placed in which section. The base has 30%. The base plus IOVF at 27%, but the last one, it says IOVF only has 32% of records in this, and we would like to reduce this number, the IOVF usage, because that again that increases the IO and that reduces the performance of your DEDB. Okay, the next slide, please. Okay, this is the segment IO analysis report. It just gives you the IO statistics about the different segment. I'll not go in detail, but 2 of the segments we can see it takes they have the physical IO it takes are a lot. The maximum goes to 1700 and the average is 1.17. Possibly because of presence in IOVF section and having long twin chain. At the end, it also gives us a snapshot of a record IO. It averages 4.7 and the maximum goes to 1713, and for which and the root IO, I mean, those number increases as the synonym chain increases basically. Next slide, please. Okay, so we have seen certain snapshot from the analyzer report and certain aspects. They point us that there might be some issue with the DEDB, which is slowing down some things. And these using threshold is a very good way to keep in check all those criteria which can enter in your DEDB. And these are the snapshot. These are the threshold which are being supported by a BMC analyzer tool, and similar thresholds are available in other analyzer tool as well. So there are 4 categories by which these thresholds can be categorized. If you want to monitor something in free space, if you want to monitor something with respect to IO or wrap usage or even overflow characteristic, you can use these thresholds in the BMC analyzer product, and then it will give you an exception once that particular threshold is reached. Anshu, can you go to the next slide, please? Yeah, so I have just taken one example from each section of the threshold, and I'll just talk about it in a minute. How we can use these thresholds to pointer exceptions in our DEDB that this particular threshold is breached, and it might be a good time for you to do some more analysis. So for example, for the first one, it says IOVF free space %. That means that we want to maintain at least this much free space in our DEDB. For example, IOVF free space % is 40 in this case. It says that if the free space in the IOVF it reduces than 40%, then you should throw an exception, and then you will get an exception. In this case, like total available independent overflow is below 40%. Similarly, let's say I'll go at the third one, which says synonym maximum chain. It says that you want to keep a check on the synonym chain, the maximum synonym chain length, and I don't want my area to have more than 5 synonym chain length. I'll put this exception SCM equal to 5, and then once the synonym chain increases, it will give me an exception. So based upon these threshold and based upon the exceptions I receive over this threshold, I can review other reports and take an action which is required, probably running some tool which will help me to reclaim some free space movement of records from IOVF to other area. Until next slide, please. Okay, so we have seen certain criteria which can really you have to monitor those criteria to understand if your DDB is tuned or not, if it's working fine, or it will work fine, but there is a possibility of any issue in future. And then there are certain tools which you have to use based upon those reports and those exceptions. For example, the BMC React tool or any other React tool, basically, to reclaim the free space. So if I talk about the React tool, so BMC React tool or any React tool, basically, it will what the intention is that you want to eliminate the fragmented free space and scrap from the area. Then you want to move as many segments from the IOVF into the DOVF and the RAD part. So that is what React does, and it frees up your IOVF area. It brings up your DDB in a better health than the previous state. So BMC React, I mean, they use a patented technology. It only identifies those unit of work based upon users' criteria. Those has to be React. And it does not reorg all the unit of works, but the user can set some criteria, and based upon those criteria, a particular UW gets reorganized. They were saving a lot of time. Next slide, Anshul. Okay, so the last thing is that we should also consider using secondary index in our DDB. At times, accessing a particular segment out of the order of root segment key is faster. It can reduce some IO in otherwise. Using a secondary index, it definitely reduces the segment retrieval time depending upon your application. And we also have we can also use a secondary index database as a standalone database. It's kind of a subset of your DDB, and the application can directly access that particular DDB as a secondary index DDB. A secondary index DB as a standalone database, and that will definitely reduce the number of IO, thereby increasing the performance of your DDB. Anshul, next slide, please. Yeah. So these are just a list of the acronyms we have used in our presentation for your reference. Anshul, next slide. So that was all from us. Thanks a lot for joining the session. Please feel free to ask any question and submit your feedback on this link. And session is 5B easy, 5BE. So yeah, okay. Tom. So your question is that these reports. Yeah. I mean, yes.
Yeah. So I'd just like to say thanks very much, guys, Anshul and Ativia, for doing that presentation. Very comprehensive, I think. Now, yeah, so the first question, maybe if I just sort of mention that. So all I was going to ask was some of those performance reports that you had in the latter half of the presentation, presumably they're via certain analyzer utilities.
Yes, that's right, Tom.
Yeah, and I guess you've got various products available for those, and then there's probably other vendors as well, of course. But
yes.
Yeah, okay. So I'd like to open up questions to the room, really. So I'm just asking everybody to unmute. It's coming up to 10 o'clock, so we've got about 5 minutes, I say, because we've got a break now. So I think if we have a 5-minute talk, if anybody has got any questions, there's actually there's about 28, 29 people, up to 30 people in the room, which is a record for us. So that's great. So have you got a question to ask Anshul and Ativia, then please do unmute yourself now and ask the question. They're over to you. I mean, I've got probably another question. And obviously, some of those, it's a balancing act, isn't it? Some of the performance attributes, depending on how much space you've got overall available. And certainly from my perspective, when I try and do the management and performance, we're always trying to do the not necessarily use IOVF, but sometimes we have to. So it kind of depends on the database type and what the performance is. So definitely try and keep your IOVF lower if you can, but sometimes you might actually use it if it was, say, a bucket database, which the performance doesn't matter that much on. So there are some good debate items on there, probably for future. But IO, keeping the IO a minimum is definitely what you were saying through the presentation, which I think is really good. Yeah. So have you got any other questions for Aditya and Anshul? Please just unmute yourself and then ask your question. Don't be shy. No, well, if that's it, then
Tom, probably we might have done a great job by explaining this in very detail, or we might have done a very poor job. Nobody
no, I think
not asking questions.
No, but I think sometimes some people maybe they don't know. There's a broad audience probably, and I don't know how many people will have had experience of FastPath. It might be the first time that they have had or not. So I think we'll probably have a wider audience in terms of FastPath usage. Certainly in the UK, there's not that many users, but there will be in Europe and Scandinavia and across the piece. And we've got some Scandinavian users as well on this call. But just if anyone does want to shout, then please do so. But I'll just summarise, and Ativia just said this before. If we've got feedback, then use the QR code here. And the section is 5BE. I thought it was a really good presentation on both of fronts. So you definitely got my thumbs up. We thank everybody in the room for joining in this session. As I said, we had a record number, which is fantastic. And in terms of protocols, we'd just like to give you a virtual round of applause, Anshul and Ativia, for that presentation. Virtual round of applause, everybody. Well done. And just say if the slides will be, have we got the slides available to load up yet, or are we going to do that?
It's already
fantastic. I thought they were, yeah. So the slides are available, everybody. If you want to download them, then just click on the agenda link for this title of this conference, and then you can click down on the and load up the file for the foils, the slides. So I'd just like to just thank you once again, both of you, for doing that. Anshul and Ativia, that was really good. And thank you everybody for joining. There is another, the final session for this conference will be good, better and best. Are you buffering IMS efficiently? And that will be by Susie Wendler and somebody else as well. So that will be at 2 p.m. UK time. So without further ado, I'd like to say thanks everybody for joining and have a good rest of your day.
Thanks.
Thank you.
Thanks everybody.
Bye-bye.
Thank you. Thanks, guys.